For most of human history, we believed that the universe around us was uniform, that our corner of space was in no way exceptional. Yet modern astronomy has revealed something astonishing. Our galaxy exists inside a colossal void, a region of the cosmos almost unimaginably empty. This discovery, confirmed in the early 2010s, challenges some of the most fundamental assumptions of cosmology. Known as the KBC Void, named after its discoverers Ryan Keenan, Amy Barger, and Lennox Cowie, this immense region stretches billions of light-years across and contains about 20% less matter than expected. To picture this, imagine a vast cosmic desert in which galaxies are scattered sparsely like isolated oases across a sea of nothingness. This revelation did not come easily or by accident. For years, astronomers had been meticulously cataloguing the positions and distances of tens of thousands of galaxies, attempting to map the large-scale structure of the universe. When Keenan and his colleagues examined data from several galaxy surveys, they noticed something peculiar. The density of galaxies near our own Milky Way was far lower than what theory predicted. The discrepancy wasn't minor, it was enormous. Across every direction they looked, the number of galaxies was consistently reduced by about 1/5. The pattern extended for over 1 billion light-years, forming what appeared to be a gigantic, underpopulated bubble, with Earth positioned surprisingly close to its centre. Initially, the scientists suspected an error. Perhaps the telescopes had overlooked distant, faint galaxies, or maybe the calibration of redshift data had gone wrong. But multiple independent observations confirmed the finding. They cross-checked surveys from different instruments, examined various regions of the sky, and even used alternative methods to estimate cosmic density. Each analysis returned the same result: a vast underdense region encompassing our galactic neighbourhood. The magnitude of this emptiness was unlike anything previously observed, defying what cosmological models considered likely. In the standard view of the universe, matter should appear roughly uniform when averaged over sufficiently large scales. Clusters, filaments, and smaller voids are expected, of course, but a region this large and this depleted in matter lies far beyond normal variation. Computer simulations of the universe's evolution, starting from conditions just after the Big Bang, almost never produce voids of this magnitude. When they do, it requires extremely improbable starting conditions, so rare that statistically, such a structure should not exist anywhere within the observable universe. And yet, here we are. The existence of the KBC Void forces us to reconsider how the cosmos behaves on its grandest scales. If our location is atypical, then every measurement we make of cosmic expansion, of galaxy motion, or even of the universe's age might be subtly distorted by our perspective. The emptiness around us acts like a gravitational lens in reverse, altering how we perceive the rest of the cosmos. It changes how light travels, how galaxies appear to move, and how fast we think space itself expands. The idea that our cosmic neighbourhood could bias our understanding of the universe introduces deep uncertainty into measurements we once considered reliable. One of the first clues that something was amiss came from an ongoing puzzle known as the Hubble tension, the fact that different methods of measuring the universe's expansion rate give inconsistent results. Astronomers using distant cosmic background radiation calculate one value, while those studying nearby supernovae and galaxies measure a noticeably faster expansion. For years, the difference resisted explanation. But if we live inside a vast underdense region, it could all make sense. Space here would expand slightly faster than average because there is less gravity pulling inward. In this interpretation, our measurements aren't wrong, they're simply local. We are observing the universe from within a bubble that expands quicker than its surroundings. This realization is both elegant and unsettling. It solves one problem while creating another. If we reside in such an exceptional place, does that mean the cosmological principle, the assumption that the universe looks the same everywhere on large scales, is false? Science has always moved us away from the idea of specialness. Earth is not the center of the solar system, the sun is not the center of the galaxy, and our galaxy is not the center of the universe. Now we face a paradoxical twist. We may occupy one of the rarest places in existence, yet even as it challenges our sense of cosmic normality, the KBC Void offers a rare gift to science. By existing within one of the largest natural laboratories for dark energy and cosmic expansion, We have an unparalleled vantage point to study how the universe behaves where gravity grows weak and emptiness dominates. The discovery redefines what it means to look outward. We are not floating in a crowded cosmic metropolis, but rather in a vast silent plane of space where galaxies are few and darkness stretches endlessly between them. The more we understand this strange environment, the more it forces us to rethink our most basic assumptions about the cosmos and our place within it. When scientists first tried to chart the large-scale structure of the cosmos, they imagined a smooth, even distribution of matter galaxies sprinkled more or less uniformly across an infinite expanse. But as telescopes improved and survey data multiplied, that picture began to shatter. The universe revealed itself not as a homogeneous mist of stars, but as a vast web-like architecture of clustered galaxies, elongated filaments, and enormous empty spaces. These voids, though invisible to the naked eye, define the skeleton of the cosmos just as much as the galaxies themselves. Among them, one stands out with extraordinary size and significance: the KBC Void, the immense underdense region that encompasses our local galactic neighbourhood. Mapping such a colossal emptiness required an enormous feat of data gathering. Astronomers used galaxy redshift surveys to measure the distances of tens of thousands of galaxies, recording how light from each one was stretched by the expanding universe. By compiling these redshifts into three-dimensional maps, researchers could visualize where matter was concentrated and where it was sparse. In the process, they discovered a striking pattern. Galaxies tend to align along immense cosmic filaments, forming a tangled network hundreds of millions of light-years long. Between these filaments lie immense bubbles of relative nothingness, the cosmic voids. Each void is a vast region where galaxies are fewer, stars rarer, and dark matter less dense. The KBC Void, however, dwarfs most others, stretching roughly 2 billion light-years across, making it one of the largest known structures in the observable universe. The first step in confirming its existence involved assembling data from several large-scale surveys, including the 2-micron All-Sky Survey, (2MASS), and the Sloan Digital Sky Survey, (SDSS). These programs scanned enormous swaths of the sky, cataloguing millions of galaxies and providing a statistical backbone for measuring cosmic density. When the data were analysed, the numbers painted an unexpected picture. Within about 1 to 2 billion light-years of the Milky Way, the average galactic density was roughly 20% lower than the universal mean. The underdensity wasn't limited to a single direction. It extended across nearly every region of the sky. To visualize this, researchers constructed radial density profiles, showing how galaxy concentration changes with distance. The resulting graph revealed a gradual dip near our position, followed by a slow rise toward higher densities at greater distances. This smooth pattern indicated that the Milky Way, along with its neighboring galaxies, resides near the center of a vast underdense region. The structure wasn't a sharp-edged bubble, but rather a gently varying depression in the cosmic landscape, like a valley surrounded by distant mountain ranges of galaxies. Confirming this structure required not only optical surveys, but also observations in other wavelengths. Radio astronomy offered another perspective. By tracking neutral hydrogen emissions, scientists could detect galaxies obscured by dust or too faint for visible light telescopes. The results from radio surveys reinforced the same conclusion. Additionally, infrared observations helped identify galaxies hidden behind the Milky Way's own disk, filling in gaps in the map and ensuring the void wasn't an artifact of incomplete data. Every independent dataset pointed to the same reality. The universe around us is less crowded than average. The implications of this realization were profound. If we live inside a giant cosmic void, then the gravitational pull we experience locally would differ from what a truly average observer would measure elsewhere. Gravity within a void is weaker, meaning space there expands slightly faster. The light from distant galaxies traveling through the underdense region would be subtly stretched, altering redshift readings and potentially leading astronomers to miscalculate cosmic distances. What had once seemed like minor discrepancies in measurements could now be explained as natural consequences of our cosmic geography. This insight prompted a re-examination of nearly every observational dataset used in cosmology. Astronomers had long relied on the assumption of large-scale uniformity, the cosmological principle to interpret data. If our surroundings violated that assumption, even slightly, then every inferred property of the universe, from its expansion rate to its estimated age, might need reconsideration. Some scientists resisted the notion, arguing that such a large void seemed statistically improbable. According to computer simulations of cosmic evolution, regions of such extreme underdensity should be vanishingly rare. Others countered that nature often surprises us, and our simulations might not yet capture the full complexity of cosmic structure formation. The universe, after all, has proven itself far more intricate than our mathematical models often allow. Mapping the KBC Void also demanded refinement in how scientists visualize large-scale cosmic features. Traditional maps of the universe were often flattened projections, distorting distances and orientations. To fully grasp the void's scale, astronomers began constructing three-dimensional reconstructions using volumetric data visualization. These digital models allowed them to fly through the universe virtually, tracing filaments, walls, and cavities. The KBC Void appeared as a gently sloping basin, with our galaxy sitting near the middle, surrounded by distant concentrations of galaxies marking the edges. What makes the mapping of emptiness so remarkable is that it depends not on what we see, but on what we don't. Each absence of light, each gap between galaxies, contributes to the map as much as any shining star. In this sense, cosmology becomes an art of interpreting darkness. The vast empty regions speak as loudly as the luminous clusters, telling a story about gravity, expansion, and the delicate balance between matter and nothingness. Through painstaking observation and analysis, scientists have turned that silence into data, revealing the contours of the invisible. As a result, the once assumed uniform universe now appears as a dynamic, uneven fabric, an intricate balance of fullness and void. Mapping this emptiness has not only redrawn our cosmic neighborhood, but also reminded us that the absence of matter can be just as meaningful as its presence. In the grand geometry of the cosmos, it is the empty spaces that define the structure of everything we see. The discovery of the KBC Void sent ripples through the scientific community because it seemed to contradict the very framework that modern cosmology rests upon. The standard model of cosmology, often called the lambda cold dark matter model, or LCDM, has been the dominant explanation for the structure and evolution of the universe for decades. It describes a cosmos composed mostly of dark energy and dark matter, governed by Einstein's general relativity, and expanding smoothly from an initial hot, dense beginning. Within this model, the large-scale universe is assumed to be homogeneous and isotropic, meaning that, when averaged over hundreds of millions of light-years, it should look the same everywhere and in every direction. The discovery that our region of space may be dramatically underdense violates that core assumption. If the area we inhabit is not representative of the cosmos as a whole, then many of the measurements that depend on that assumption could be subtly distorted. The implications reach deep into the foundations of cosmology, forcing scientists to question not only their observations, but the very principles that underlie their models of the universe. When Keenan, Barger and Cowie presented their findings, many researchers were initially skeptical. The LCDM model had been incredibly successful in explaining everything from the cosmic microwave background radiation to the formation of galaxies and the observed distribution of matter. Its predictive power made it the backbone of modern astrophysics. Yet, as evidence of the KBC Void accumulated, it became harder to dismiss the anomaly as mere statistical noise. The existence of such a massive underdensity might not destroy the LCDM model, but it certainly stretched its assumptions to the breaking point. The problem lies in probability. According to standard cosmological simulations, the universe should contain many voids regions with lower matter density, but their typical sizes are measured in tens or perhaps hundreds of millions of light-years. A void spanning over 1 billion light-years with an underdensity as deep as 20% is statistically extraordinary. In simulated universes that follow LCDM physics, such structures are almost non-existent. They can occur, but only with probabilities so small that finding ourselves in one seems cosmically coincidental. This raises a troubling philosophical question. Are we simply extraordinarily lucky or unlucky to be living in such a rare location, or does our very presence here hint that our cosmological model might be missing something? The challenge is that the standard model depends heavily on the cosmological principle, the belief that no location in the universe is special. This principle is not merely aesthetic, it's practical. It allows cosmologists to simplify their equations and treat the universe as a single coherent system. Without it, the calculations of cosmic expansion, the interpretation of redshifts, and the derivation of distances become far more complex. If the universe is not uniform on the larger scales, then light travelling through different regions may experience different expansion rates, leading to systematic biases in the data astronomers collect. In that case, some of our most precise measurements, such as the Hubble constant, which describes how fast the universe is expanding, could be subtly skewed by our local cosmic environment. The Standard Model has no mechanism for producing a void as large as the KBC1 under ordinary conditions. Dark energy, the mysterious force driving the universe's accelerated expansion, acts uniformly across space. Gravity, in turn, tends to pull matter together rather than push it apart. To carve out a region this vast and underdense would require either extremely unusual initial fluctuations in the early universe or some new physical process that amplifies those differences over time. Some researchers have speculated that variations in dark energy density or exotic forms of dark matter could be responsible. Others suggest that general relativity itself might behave differently on extremely large scales, subtly modifying cosmic dynamics in ways that allow for greater regional variations. These possibilities are controversial because they imply physics beyond the established model. For decades, cosmology has operated under the reassuring assumption that the universe obeys the same rules everywhere. The KBC Void, however, threatens that comfort. If its existence cannot be reconciled with the Standard Model, then something fundamental about our understanding of the cosmos must change. Yet this tension is not necessarily destructive. It could be revolutionary. History shows that when observations defy established theory, progress follows. The unexpected motions of Mercury led to Einstein's theory of relativity. The failure to detect the expected amount of visible matter led to the concept of dark matter, and the discovery that the universe's expansion is accelerating gave rise to dark energy. Perhaps the KBC Void will serve as another catalyst, pushing physics toward a deeper, more complete framework. Some scientists have begun exploring modified cosmological models that allow for large-scale inhomogeneities. One class of such models, known as Lemaitre-Tolman-Bondy (LTB) models, describes universes that are spherically symmetric but radially varying in density. In such a universe, observers located near the center of a large void would see expansion rates that differ from those observed from denser regions. These models can reproduce certain cosmological observations without requiring any exotic new physics, though they do come at a philosophical cost. They place us in a privileged position. Still, the very fact that these alternatives are being taken seriously shows how deeply the KBC Void has unsettled cosmologists. The void forces scientists to confront the possibility that our picture of the universe's structure is incomplete, and that the assumptions underlying our equations may no longer suffice. The Standard Model remains an extraordinarily successful theory, but like all scientific frameworks, it must bend or evolve when new evidence demands it. The KBC Void stands as a reminder that the universe still holds surprises vast enough to shake even our most trusted ideas. It suggests that what we perceive as emptiness might, in fact, be the key to unlocking the next great transformation in our understanding of reality itself. The revelation that our galaxy may sit inside an enormous cosmic void carries deep consequences for how we interpret the universe's expansion. The concept of an expanding universe is one of the central pillars of cosmology, first proposed in the early 20th century when astronomers observed that distant galaxies were receding from us. This motion, described by the Hubble-Lemaitre law, suggests that space itself is stretching, carrying galaxies apart like dots on the surface of an inflating balloon. The rate of this expansion, known as the Hubble constant, is fundamental to understanding cosmic history, yet measuring it has proven far more complicated than anyone expected. The so-called Hubble tension, the persistent disagreement between different measurement methods, remains one of modern science's most perplexing puzzles. If the KBC Void truly exists, it could provide a natural explanation for this tension. The logic is simple but profound. If we live in a region with less matter than average, gravity's inward pull is weaker here. With less mass to resist expansion, local space should stretch slightly faster than the universe as a whole. Consequently, When we measure the expansion rate using nearby galaxies and supernovae, those residing within or close to our underdense region, we would observe a higher Hubble constant than one derived from more distant measurements that sample the cosmic average. This difference could easily account for the roughly 10% discrepancy that has confounded cosmologists for years. The local expansion effect isn't just theoretical. Mathematical models show that an observer located near the centre of a large void would see light from nearby galaxies redshifted more than expected, giving the illusion of an accelerated local expansion. The farther out one looks, beyond the void's boundary the effect diminishes, gradually approaching the global expansion rate. In essence, our cosmic environment might be fooling us into thinking the universe is expanding faster than it truly is. The beauty of this idea lies in its simplicity. It doesn't require new particles or exotic physics, just a careful reconsideration of where we happen to be. Yet, as elegant as it sounds, verifying the effect is extraordinarily difficult. Measuring cosmic expansion depends on a ladder of distance indicators, each with its uncertainties. Astronomers rely on Cepheid variable stars, type Ia supernovae, and other so-called standard candles to gauge distances, while redshift provides the corresponding measure of velocity. Any local irregularities in density or gravitational potential can subtly distort both quantities, making it hard to disentangle the true rate of expansion from local biases. To complicate matters, the boundary of the KBC Void is not a sharp edge, but a gradual transition. This means that galaxies at intermediate distances feel partial influence from both the underdense interior and the denser cosmic exterior, creating a smooth but complex gradient in expansion rate. Modelling that gradient requires precise knowledge of how matter is distributed on scales of hundreds of millions of light-years, an observational challenge at the very limit of current technology. Despite these obstacles, several independent studies have tested the void hypothesis as a potential resolution to the Hubble tension. Some have simulated the effect using inhomogeneous cosmological models, finding that a void of the KBC's estimated size and depth could indeed produce a local expansion excess of the observed magnitude. Others, however, argue that the numbers don't quite add up. They claim the void would need to be even larger or emptier to explain the full discrepancy. This debate remains unresolved, illustrating how sensitive cosmological conclusions are to small variations in initial assumptions. Still, the notion that our local environment could distort our cosmic measurements carries profound philosophical weight. For decades, cosmologists have treated their observations as windows into the universal truth, as though measuring from any point in space would yield the same results. The KBC Void reminds us that perspective matters. Just as standing in a valley changes one's view of a mountain range, our position in a vast underdense region may alter our perception of cosmic expansion. This doesn't mean our observations are wrong. It means they are context-dependent. The universe we see may be shaped by the structure we inhabit. If local expansion bias turns out to be real, it could elegantly reconcile two seemingly contradictory views of the cosmos. Measurements from the cosmic microwave background, our snapshot of the early universe, reflect the global average, while nearby supernova observations capture a region expanding slightly faster. The mismatch, rather than signalling a flaw in our physics, could simply reveal that the universe is more textured than we assumed. It would mean that the grand cosmological principle, though approximately true, hides subtle variations that matter on scales of billions of light-years. In this sense, the local expansion mystery is not just a technical issue, but a reminder of our cosmic humility. Every measurement we make, no matter how precise, is coloured by our place in the universe. Our instruments may reach across billions of light-years, yet our perspective remains inevitably local. The emptiness surrounding us might not only shape how space expands, it might also shape how we understand the very nature of reality. Few scientific disagreements have sparked as much debate in modern cosmology as the Hubble tension. It is a deceptively simple problem. When astronomers measure how fast the universe is expanding, they consistently arrive at two conflicting numbers. Both sets of measurements are precise, both are performed by experts using independent methods, and yet they disagree by enough to suggest that something fundamental may be missing from our understanding of the cosmos. The discrepancy centers on the Hubble constant, the number that quantifies the rate of cosmic expansion in kilometers per second per megaparsec. measurements based on the cosmic microwave background, the faint afterglow of the Big Bang, yield a lower value, around 67. Meanwhile, measurements based on observations of nearby supernova and variable stars give a higher value, around 73. The gap between these results may seem small, but in cosmology it is vast large enough that random error alone cannot explain it. Either one of these methods is flawed, or the universe behaves differently on local and global scales. This is where the KBC Void enters the discussion. If our galaxy resides in a massive underdense region, that emptiness could naturally account for the higher local expansion rate. In a region with less matter, gravity's restraining pull is weaker, allowing space to expand a little faster. Observers within that region would therefore measure a larger Hubble constant than those looking at the universe from a more typical or denser vantage point. The beauty of this explanation lies in its parsimony. It requires no new physics, no mysterious interactions between dark matter and dark energy, only an honest acknowledgement that our cosmic neighbourhood might not represent the average conditions of the universe. From a certain perspective, the Hubble tension could be seen not as a cosmic inconsistency, but as a simple geographic illusion on the largest possible scale. Yet not everyone finds this argument convincing. Critics point out that even if the KBC Void were as large and deep as measurements suggest, its effect on the Hubble constant might be too small to account for the full discrepancy. The predicted increase in the local expansion rate, they argue, would be only a few %, while the observed difference is closer to 10. Others counter that our estimates of the void's depth remain uncertain. If it is even slightly more underdense than current models assume, the numbers could align. The debate remains open, reflecting the difficulty of precisely quantifying matter distribution across billions of light years. What makes the Hubble tension so troubling is that both competing methods appear robust on their own. The cosmic microwave background measurement, derived from data collected by the Planck satellite, relies on the early universe's imprint and the physics of sound waves travelling through primordial plasma. It tells us how fast the universe was expanding just 380,000 years after the Big Bang, then extrapolates that rate forward in time using the equations of the standard cosmological model. The local measurement, by contrast, uses a distance ladder that builds from parallax to Cepheid variable stars to type Ia supernovae. These techniques are well tested and have been refined for decades. If both methods are sound, then the only logical conclusion is that the universe itself is not uniform enough for a single expansion rate to apply everywhere. This would be a profound realization, undermining the cosmological principle that has guided astronomy for a century. The KBC Void hypothesis fits elegantly within this framework, but it also highlights an uncomfortable truth about our perspective. We cannot escape the influence of our environment. Just as a person living in a valley might wrongly assume the world is flat because the surrounding hills block their view, we might be misjudging the universe's true expansion rate because we happen to live inside a cosmic lowland. In recent years, alternative explanations for the Hubble tension have multiplied. Some physicists suggest that dark energy's strength may evolve over time, accelerating expansion differently in the early and late universe. Others propose interactions between dark matter particles, new types of neutrinos, or even small modifications to general relativity itself. Yet each of these ideas introduces new parameters or entities, complicating the simplicity of the standard model. Compared to those exotic options, the void hypothesis is refreshingly down to earth. It does not demand a new force of nature, merely an acknowledgement that our local cosmic geography is peculiar. If future surveys confirm that we live within an underdense region of the right size and depth, the Hubble tension could vanish overnight. However, if improved observations fail to detect such a void or find that its influence is insufficient, then cosmologists will be forced to look deeper, perhaps confronting the possibility that the universe's fundamental laws are incomplete. Either outcome promises a leap forward in understanding. What is certain is that the Hubble tension has already reshaped the landscape of cosmology. It has turned a single numerical disagreement into a philosophical reckoning about how we know what we know. Are our cosmic measurements objective truths, or are they inevitably coloured by our position in space and time? The answer to that question could redefine not only how we measure the universe, but how we conceive of our place within it. The void around us, once dismissed as an anomaly, may prove to be the very key that unlocks the mystery of cosmic expansion, and in doing so, It reminds us that even in the most advanced science, perspective is everything. To imagine what it means to live inside a cosmic void, we must first understand what a void really is. The word suggests complete emptiness, but in cosmic terms, it simply means a region where matter is less concentrated than average. A void is not a perfect vacuum. It still contains galaxies, gas, dark matter and radiation, just in smaller amounts. These regions make up the majority of the universe by volume, occupying the spaces between immense walls and filaments of galaxies. In this sense, the cosmos resembles a sponge or a web, where dense threads of matter surround vast hollow bubbles. Our own galaxy lies within one of those hollows, the KBC Void, which stretches across nearly 2 billion light-years. Life inside a void is not dramatically different from life anywhere else. We do not feel the emptiness, nor does it alter the basic physics that govern our world. Yet its influence extends subtly but profoundly over cosmic time. Because matter is scarcer, gravity is weaker, and the local expansion of space proceeds more rapidly. This means galaxies within a void drift apart faster than those in denser regions, and the faint glow of distant light appears slightly redder as it crosses the expanding emptiness. To an astronomer, these differences are small but measurable clues, written into the patterns of the universe's structure. Inside a void, galaxies tend to be fewer and more isolated. They grow differently than their counterparts in crowded clusters. Without frequent gravitational interactions, their evolution is gentler, slower, and often cleaner. Many void galaxies are rich in gas and continue forming stars long after cluster galaxies have exhausted their fuel. Their shapes are less distorted by collisions, and their spiral arms remain pristine. Observations show that these galaxies often have bluer colors and simpler structures, hinting that environment plays a quiet but decisive role in shaping cosmic life. The emptiness surrounding them shields them from the chaotic violence that reigns in denser parts of the universe. Voids also serve as natural laboratories for testing cosmological theories. Because they are regions where matter density drops below the cosmic average, they amplify the effects of dark energy, the mysterious force responsible for accelerating expansion. In dense areas, gravity dominates, pulling matter together. In voids, where gravity is weaker, dark energy becomes more visible in its influence. Studying how galaxies move within and around voids can therefore reveal how dark energy behaves on large scales. In this way, emptiness becomes a tool for probing the unseen forces that shape reality. The KBC Void, if confirmed as one of the largest of its kind, offers an extraordinary opportunity to test these ideas. It allows scientists to observe how local structure affects the apparent rate of expansion, and to refine measurements of cosmic distances. It also challenges our psychological perspective. We are accustomed to thinking of ourselves as living in a typical place, yet the data suggest otherwise. Our galaxy's home may be one of the rarest regions in the cosmos, a nearly billion light-year wide zone of gentle stillness amid the cosmic storm. This realization alters not only our measurements but our metaphors. We have always imagined humanity existing in the midst of grandeur, a galaxy among countless others in a uniform sea. But to live inside a void is to inhabit the universe's quiet place, a vast interlude between its great structures. It is a reminder that emptiness is not the absence of meaning, but another form of structure, one that shapes everything by what it lacks. In that emptiness lies a story written in silence, how the universe expands, evolves, and reveals its deepest laws not through the presence of matter, but through the places where matter is missing. At the heart of modern cosmology lies a silent struggle between two cosmic forces, gravity and dark energy. These invisible agents shape the fate of the universe, pushing and pulling on the grandest scales imaginable. Gravity, familiar yet mysterious, draws matter together, binding galaxies, stars, and planets into coherent systems. Dark energy, equally enigmatic, works in the opposite direction, driving the expansion of space itself. For billions of years, the contest between these forces has sculpted the cosmic landscape, carving out clusters, filaments, and vast voids. Inside regions like the KBC Void, the balance tips decisively toward dark energy, and its influence becomes more apparent. Gravity's strength depends on matter density. Where galaxies and dark matter are abundant, gravity's pull is strong, slowing expansion and drawing structures inward. But in a void, the low density means gravity's restraining power is weak. There, the fabric of space stretches more freely, and the subtle push of dark energy gains the upper hand. This is why voids expand faster than denser regions, and why the light that passes through them experiences an extra redshift. It is literally riding the wave of space growing more quickly than average. In this sense, voids act like natural accelerators of cosmic expansion, amplifying the work of dark energy. Yet dark energy itself remains a profound mystery. Its name is a placeholder for an unknown phenomenon that accounts for roughly 70% of the total energy content of the universe. It is not a force in the traditional sense, nor a substance we can detect directly. Instead, it appears to be a property of space itself, a constant energy density that remains even as the universe expands. This idea, first proposed by Einstein as the cosmological constant, suggests that empty space is not truly empty, but filled with a kind of latent pressure that pushes everything apart. Voids, being dominated by this emptiness, provide the best natural environment to observe dark energy's effect. The tension between gravity and dark energy defines the universe's destiny. In the early cosmos, gravity ruled supreme, drawing gas and dark matter into the first stars and galaxies. But as expansion continued and matter thinned out, dark energy began to dominate. The universe transitioned from decelerating to accelerating, a change first detected in the late 1990s through distant supernova observations. This discovery earned a Nobel Prize and transformed cosmology, yet we still lack a clear explanation for why dark energy exists, or why it has the strength it does. Studying cosmic voids may hold the key. Because gravity is weaker inside them, the accelerating influence of dark energy becomes easier to isolate. The movement of galaxies around void edges, the stretching of light passing through their centers, and the subtle patterns in the cosmic microwave background all carry signatures of this hidden energy. Observations suggest that voids behave as miniature universes within the larger whole, each expanding slightly faster, each tracing the interplay of attraction and repulsion that defines the cosmos. The KBC Void offers a particularly interesting test case because of its immense size. If dark energy acts uniformly everywhere, the void's expansion should follow precise mathematical predictions. If it doesn't, if the expansion rate within the void deviates more than expected, then dark energy might not be constant after all. It could vary with environment or time, implying new physics beyond the standard model. In that case, voids could reveal something profound about the structure of space itself. The conflict between gravity and dark energy is not merely a scientific puzzle. It is a philosophical one. Gravity represents connection, the universal tendency of things to come together. Dark energy represents separation, the drive of space to expand and isolate. The universe exists in the tension between these opposites. Within dense clusters, gravity's dominance produces warmth, light, and structure. Within vast voids, dark energy reigns, producing silence and distance, and yet both are essential. Without gravity, nothing would form. Without dark energy, everything would collapse. The two together create a cosmos that grows, evolves, and changes. In the end, the universe's story may hinge on which of these forces wins the long contest. Billions of years from now, if dark energy continues to dominate, galaxies will drift apart until the night sky grows dark and empty. The great cosmic web will dissolve into isolation, and only the faintest whisper of radiation will remain. To study the voids today is to glimpse that distant future, to see what the universe might become when gravity finally yields to expansion. Inside the KBC Void, we are living in a preview of that destiny, a quiet realm where dark energy already holds sway, shaping the emptiness that surrounds us. The universe, when seen on its largest scales, resembles an intricate web woven from both matter and emptiness. This colossal structure, aptly named the cosmic web, emerged from the primordial fluctuations of the early universe and now stretches across billions of light years. It consists of vast filaments of galaxies and dark matter that intersect at dense knots called clusters, enclosing enormous voids like bubbles in cosmic foam. Every galaxy, including our own, is part of this grand interconnected pattern, moving along invisible gravitational highways shaped by the web's geometry. From a distance, it is a breathtaking sight, luminous strands spanning the darkness, binding the cosmos into a single vast design. The cosmic web's existence was first hinted at in the late 20th century, when astronomers began mapping galaxy positions using deep redshift surveys. Instead of finding a uniform scatter, they uncovered immense walls and chains of galaxies forming continuous filaments. Between them lay enormous voids regions nearly devoid of bright galaxies. Subsequent computer simulations confirmed that this was not coincidence. When the universe began, tiny fluctuations in density were imprinted on the sea of matter and radiation. Over billions of years, gravity amplified these fluctuations, drawing matter into sheets and filaments while leaving behind underdense cavities. The web is therefore a fossil record of cosmic evolution, frozen evidence of how structure arose from simplicity. Its filaments are not just strings of visible galaxies, but vast rivers of dark matter, invisible to our eyes yet responsible for most of the web's mass. Dark matter's gravitational pull acts as scaffolding upon which galaxies form, tracing its hidden contours. Each node of the web where filaments meet contains enormous clusters of galaxies, gravitationally bound and rich in hot gas. The spaces between them, the voids, account for most of the universe's volume. Though seemingly empty, these regions are the quiet counterpart to the web's brilliance, defining its shape through contrast. Without the voids, there would be no visible structure. Without the dense filaments, there would be no pattern to the emptiness. The cosmic web is dynamic. Galaxies flow along its filaments, slowly migrating toward the massive nodes where gravity is strongest. This motion creates a kind of cosmic traffic, with matter funneling inward and leaving behind expanding voids. Our own Milky Way participates in this process, drifting along a filament toward a gravitational center known as the Great Attractor. The entire dance unfolds over billions of years, a slow-motion choreography of gravity and expansion that continues even now. The web also provides an elegant context for understanding the KBC Void. Rather than an isolated anomaly, our underdense region may simply be one of the largest bubbles within this interconnected network. On smaller scales, voids merge and overlap, forming larger complexes bounded by the same filaments that connect the rest of the universe. The KBC Void might represent the ultimate expression of this process, a vast basin within the grand weave of matter, bordered by superclusters like Laniakea and Perseus Pisces. Its existence reminds us that even emptiness is part of a larger design. From a philosophical point of view, the cosmic web is one of humanity's most astonishing discoveries. It reveals that the universe is not random chaos, but an ordered tapestry shaped by universal laws. Every cluster, every filament, and every empty space contributes to the harmony of the whole. When we observe it, we are witnessing gravity's artwork, billions of years of structure formation etched into the darkness. The web is the universe's architecture, the pattern that defines both presence and absence. Yet what is most striking is how this immense design arose from the simplest beginnings. The cosmic web grew from minute quantum ripples smaller than atoms, expanded to galactic scales by the inflation of the early universe. It is a testament to how complexity can emerge from simplicity, how chaos can give birth to order. The more we map it, the more it resembles a living organism, a network of nodes and connections, flowing, evolving, and self-sustaining. In its filaments we see the paths of galaxies. In its voids we glimpse the quiet heart of creation. The cosmic web is not just the structure of the universe, it is its story, written across the deepest darkness. The vast network of galaxies we see today began as something almost imperceptibly small, tiny ripples in the energy field of the early universe. Immediately after the Big Bang, the cosmos was a hot, dense plasma of particles and radiation, uniform to an astonishing degree. Yet it was not perfectly smooth. Minuscule variations in density, only 1 part in 100,000, were scattered throughout this primordial soup. These fluctuations, born from quantum processes that occurred in the first fractions of a second, provided the seeds for all future structure. When the universe expanded and cooled, gravity began to amplify these initial irregularities, pulling slightly denser regions into knots of matter that would one day become galaxies and clusters. This transformation from uniform plasma to structured cosmos is known as the birth of cosmic structure, and it is one of the most extraordinary stories in science. The earliest evidence of these primordial variations comes from the cosmic microwave background, the faint radiation left over from the moment the universe became transparent. When satellites like COBE, WMAP, and Planck mapped this ancient light, they found tiny temperature fluctuations corresponding to regions of slightly different density. These subtle imprints are essentially the blueprint of the cosmic web. Over billions of years, the regions that were a little denser attracted more matter growing under gravity's pull, while the less dense regions expanded and thinned out, forming the great voids that now dominate cosmic volume. The result is the familiar pattern of filaments and clusters we observe today, a grand tapestry woven from quantum noise. Inflation, the rapid expansion that occurred within the first instant after the Big Bang, played a crucial role in this process. It stretched quantum fluctuations to macroscopic scales, freezing them into the fabric of space. These stretched ripples acted like tiny wells in the gravitational potential, guiding matter into the shapes we now recognize. Without inflation, the universe would likely remain too smooth for galaxies to exist. The growth of structure continued gradually as the universe aged. Hydrogen and helium gas, drawn by gravity, condensed into the first stars a few 100 million years after the Big Bang. These stars gathered into protogalaxies, whose mergers and interactions shaped the larger galaxies that followed. Dark matter, although invisible, provided the underlying gravitational scaffolding, guiding ordinary matter into place. Computer simulations show that dark matter clumps into halos that merge and form filaments, outlining the cosmic web long before visible galaxies ignite. In this way, the invisible determines the visible. Understanding this early evolution also helps explain why voids like the KBC one exist. Just as dense regions grew denser over time, the underdense regions became emptier. As matter flowed toward the filaments and clusters, the spaces between them expanded faster, carving out vast cosmic bubbles. The size and depth of these voids depend on the amplitude of the original fluctuations. The fact that our local void is so large may indicate that the early universe's fluctuations were slightly more extreme in our region than elsewhere, or that later gravitational dynamics amplified the difference. Either way, the KBC Void is part of the same evolutionary story that began with quantum ripples in the first instant of time. The birth of structure reveals a profound truth. Everything we see, from galaxies to clusters to the emptiness between them, originated from almost nothing. The cosmic web, the great voids, and even the rhythm of cosmic expansion all trace back to the faint tremors of the universe's earliest moments. That delicate interplay between chaos and order, randomness and structure, continues to define the cosmos. Every star, every galaxy, and every dark corner of space owes its existence to those first tiny fluctuations. In a real sense, the universe as we know it is the magnified echo of quantum uncertainty proof that even the smallest disturbances can create worlds. Our galaxy occupies a rather quiet corner of the cosmos. Though the night sky looks crowded with stars on the scale of the universe, we live in a remarkably sparse region. The Milky Way sits not in the bustling heart of a supercluster, but within the broad dim basin of the KBC Void, a cosmic valley surrounded by distant ridges of denser galaxy structures. This position makes our home unusual but not lonely. It simply means that the space around us contains fewer galaxies and less matter than average. When we gaze outward with telescopes, we're effectively looking from the center of a vast faint bubble that stretches for nearly 2 billion light-years. The Milky Way itself belongs to a smaller structure called the Local Group, which also contains the Andromeda Galaxy and several dozen dwarfs. The Local Group drifts within a filament of galaxies that forms part of a larger region known as the Laniakea supercluster. Laniakea spans over 500 million light-years and acts as a gravitational watershed, collecting galaxies that flow toward a central region called the Great Attractor. But beyond Laniakea's edges, the density of galaxies drops dramatically. This transition marks the beginning of the KBC Void, the enormous underdense region, in which all these structures, including our own, are embedded. From our vantage point, the boundaries of this void are invisible. Space appears uniform, and only by measuring galactic distances and redshifts do we perceive the surrounding emptiness. The fact that we happen to reside near the center of this immense cavity has important consequences for astronomy. Because the local matter density is lower, the gravitational field here is slightly weaker, allowing space to expand faster. As a result, the velocities and redshifts of nearby galaxies can appear higher than they would in a denser environment. This subtle bias affects how we estimate cosmic distances and expansion rates, contributing to discrepancies like the Hubble tension. To interpret cosmic data correctly, astronomers must therefore consider not just what they observe, but where they are observing from. In this sense, our location is both ordinary and extraordinary. It is ordinary because voids occupy most of the universe's volume, and extraordinary because the KBC Void is so large that it stands out even among them. Living inside it has no physical consequence for daily life. Gravity, light, and time behave the same as anywhere else. But on cosmological scales, our position influences the story we tell about the universe's past and future. The Milky Way's motion offers another clue to our placement within this landscape. Our galaxy is not stationary. It moves relative to the cosmic microwave background at about 600 kilometers per second. This motion results from the gravitational tug of nearby structures, the Virgo cluster, the Shapley concentration, and the Great Attractor. These distant mass concentrations lie at the edge of our underdense region, pulling us subtly toward denser territory. In other words, even while we live inside a void, we are not static inhabitants. We are travelers moving along the cosmic web, drifting from the void's interior toward its denser boundaries over billions of years. This gentle migration is part of a vast gravitational flow that shapes the universe's overall structure. To visualize our position, astronomers use three-dimensional maps showing galaxies as luminous points suspended in darkness. In such maps, the Milky Way sits amid a delicate thread of galaxies, surrounded on nearly all sides by vast empty regions. It is a humbling image. Our immense galaxy, containing hundreds of billions of stars, appears as one tiny node in a sparse network floating in an ocean of nothingness. Yet this nothingness defines the cosmic landscape as surely as the galaxies themselves. Understanding our place in the void changes how we view the universe. We often imagine ourselves as residents of a crowded cosmos, yet we inhabit one of its quietest neighborhoods. The nearest major clusters are hundreds of millions of light years away, and the spaces between them stretch for inconceivable distances. This isolation may even be beneficial for life. In denser regions, frequent galaxy interactions and intense radiation could disrupt planetary systems. In a cosmic sense, we occupy a peaceful address, shielded by emptiness from the violence of the crowded universe. The KBC Void, then, is more than a scientific curiosity. It is our home's broader environment, the context of all we see. To live inside it is to dwell in one of the universe's great calm zones, where the expansion of space itself whispers louder than the pull of gravity. When astronomers measure the rate at which the universe expands, they assume that their observations reflect a universal truth, that the same laws apply everywhere, producing consistent results regardless of where one looks from. Yet if our galaxy sits inside a vast underdense region like the KBC Void, that assumption becomes questionable. The emptiness around us can subtly distort our perception of cosmic motion, creating what scientists call an expansion bias. This bias arises not because the universe behaves differently in principle, but because our vantage point is unique. In a region with less matter, gravity's pull is weaker, and the local expansion of space proceeds slightly faster. That means observers inside such a region will measure a higher value of the Hubble constant than those outside it. The difference might seem small, but it has profound consequences for cosmology. If local measurements are biased upward by our environment, then the true global expansion rate could be lower than we think. This realization reshapes how we interpret the tension between different methods of calculating the Hubble constant. Rather than reflecting a contradiction in the laws of physics, the discrepancy may simply result from our position in the cosmic landscape. Inside the KBC Void, light from distant galaxies travels through space that is expanding a little faster than average. As it moves, it experiences an additional redshift, stretching the wavelength of the light more than it would in a denser region. When we observe that redshift and translate it into distance or velocity, we infer that galaxies are receding faster than they truly are. Over billions of light years, this subtle bias compounds, leading to measurements that overestimate the local expansion rate. To correct for this effect, astronomers must model how matter density changes with distance, mapping the gradual transition from our underdense environment to the denser regions beyond. This process requires immense precision, as even tiny miscalculations can ripple through the entire cosmic distance ladder. The expansion bias is not limited to redshift measurements. It also influences the luminosity of standard candles objects like type Ia supernovae that are used to determine cosmic distances. Because the void affects both the apparent brightness and velocity of these supernovae, it introduces correlated errors into distance estimates. When astronomers plot supernova brightness against redshift to derive the Hubble constant, the resulting curve may appear steeper than it should be. Recognizing this bias helps explain why local measurements consistently produce higher values, yet accounting for it is complex because the exact shape and depth of the KBC void remain uncertain. Some models treat the void as a smooth gradient, while others suggest it has a more irregular structure with smaller subvoids and filaments. Each interpretation changes the predicted magnitude of the bias. Moreover, cosmic variance, the natural statistical scatter in how matter is distributed, means that no single region perfectly represents the cosmic average. Even in a universe governed by uniform laws, each observer's perspective is inherently local. The expansion bias thus reminds us that measurement is never entirely objective. It is shaped by context. From a philosophical standpoint, this idea echoes through the history of science. Humanity once believed itself at the center of creation, then learned that Earth orbits the Sun, that the Sun orbits the galaxy, and that the galaxy itself drifts through a boundless universe. Now we face a subtler displacement. Our measurements of cosmic truth may be colored by the very emptiness surrounding us. We are not at the center of everything, but we may occupy a place where expansion behaves differently. This does not make our observations wrong, it simply means they are incomplete without correction for perspective. For cosmologists, accounting for expansion bias is not just a technical adjustment, but an act of intellectual humility. It acknowledges that even with advanced telescopes and precise mathematics, we see the universe from one particular location, inside one particular structure. The KBC void may be vast, but it is only one feature in an endless network of voids and filaments, each offering its own version of reality. To understand the cosmos as a whole, we must learn to see beyond our bubble, to translate our local truth into a universal one. The expansion bias is therefore both a challenge and a revelation. It shows that the universe's story looks slightly different depending on where it is told, and that our task is to reconcile those many perspectives into a single coherent view of existence. For nearly a century, astronomers have tried to measure the rate of the universe's expansion, and for nearly as long they have disagreed on the exact value. The Hubble constant, denoted H0HH is one of the most important numbers in cosmology because it determines the size, age, and ultimate fate of the universe. A small change in its value can shift the estimated age of the cosmos by billions of years, or alter predictions about its long-term evolution. Yet despite decades of technological progress, the debate remains unresolved. Two primary methods dominate the discussion, and though both are highly sophisticated, they produce results that stubbornly refuse to align. The first approach looks deep into the past. By studying the cosmic microwave background, the faint afterglow of the Big Bang, astronomers can reconstruct the universe's expansion history using the physics of the early cosmos. The Planck satellite, which produced the most detailed map of this background, found a value of about 67 kilometers per second per megaparsec. This measurement represents the global expansion rate extrapolated from the conditions of the young universe, assuming the standard cosmological model holds true. The second method looks closer to home, focusing on the nearby universe. It uses a cosmic distance ladder built from standard candles, objects whose intrinsic brightness is known. By comparing how bright these objects appear, astronomers can determine their distances and calculate the local rate of expansion. Observations of Cepheid variable stars and Type Ia supernovae consistently yield higher results, around 73 kilometers per second per megaparsec. Both methods have been refined repeatedly, with systematic errors carefully examined, yet the gap between them persists. This discrepancy, known as the Hubble tension, has become one of the most persistent mysteries in modern astrophysics. If both methods are correct within their uncertainties, then something about our understanding of the universe must be incomplete. The possibility that our galaxy resides within the KBC void offers one potential resolution. Living in an underdense region means the local expansion rate could naturally appear faster, inflating nearby measurements without requiring any exotic physics. Within the void, space stretches more rapidly due to the weaker gravitational pull of surrounding matter, subtly biasing our local observations upward. If cosmologists correct for this bias, the two conflicting values of the Hubble constant might converge. Some studies suggest that a void of sufficient size and depth could account for several percent of the difference, though likely not all of it. Others argue that the void effect, combined with small refinements in the local distance ladder, might indeed close the gap entirely. The debate is far from settled, but it illustrates how the simplest assumptions, like the idea that our region of space is average, can have profound consequences. The Hubble constant debate is not just a matter of numerical precision, it is a test of the cosmological principle itself. If the universe is truly homogeneous on large scales, then local and global measurements should agree. If they do not, either our measurements are biased by environment, or the principle of large-scale uniformity breaks down. Each possibility carries deep implications. A breakdown of uniformity could suggest that the standard model of cosmology, which has guided science for decades, needs revision. It could hint at new physics, variable dark energy, or even modifications to gravity on cosmic scales. On the other hand, if the difference stems from our local conditions, it would reaffirm the existing model while highlighting the importance of cosmic geography. Both outcomes would mark progress, reshaping how we interpret the cosmos. The Hubble debate also underscores the limits of human perspective. Every measurement we make begins from a single point in space and time. The light that reaches us carries the imprint of our position within the cosmic structure, and no observation is entirely free from that influence. Recognizing this fact does not weaken science. It strengthens it by making us more aware of the assumptions that guide our reasoning. Whether the tension is ultimately resolved through the void hypothesis, or through new discoveries about dark energy and matter, the pursuit itself embodies the essence of science. To question, to measure, and to revise our understanding when nature refuses to conform to expectation. The Hubble constant, once a simple number, has become a symbol of the universe's complexity, a reminder that even the most precise measurements are shaped by where we stand in the vastness of space. For more than a century, modern cosmology has rested on a simple but powerful assumption known as the cosmological principle. It states that, on large enough scales, the universe is both homogeneous and isotropic uniform in every direction and at every location. This principle is not a law of physics but an expression of humility, a philosophical stance rooted in the idea that no place or observer is special. It grew out of centuries of scientific progress that steadily displaced humanity from the cosmic center. Copernicus showed that Earth was not the center of the solar system. Hubble revealed that the Milky Way was not the center of the universe, and general relativity extended the lesson to space-time itself. The cosmological principle became the foundation of our models because it allowed the universe to be described mathematically with elegant simplicity. If all points in space are statistically equivalent, then the equations governing expansion, gravity, and cosmic evolution can be solved globally. Yet the discovery of vast structures such as the KBC Void forces us to reconsider how universal that principle truly is. The principle works remarkably well on paper and matches most large-scale observations. Surveys of galaxies across billions of light-years show an overall even distribution of matter when averaged over the larger scales. But locally, the universe is anything but uniform. It is a patchwork of dense clusters, sprawling filaments, and immense empty voids. The question is not whether inhomogeneities exist, they clearly do, but whether they grow so large that they undermine the assumption of homogeneity. If the KBC void is as extensive as current data suggest, then we may live in a region where the cosmological principle breaks down, at least temporarily or locally. This would not mean that the principle is entirely wrong, but rather that it is an approximation one that works on average but fails in detail. Such a realization carries profound implications. Many of the universe's key parameters, from its age to its expansion rate, are derived under the assumption of large-scale uniformity. If that uniformity is violated, even subtly, the values we calculate could shift. Our cosmological model might still be broadly correct, but our numbers might not be. The possibility that we occupy an exceptional location also touches something deeper, our enduring desire to believe in cosmic mediocrity. The principle that we are not special has guided science for centuries, and for good reason, it guards against bias. But what if the universe simply isn't uniform? What if our region really is different? Such a scenario would not reintroduce geocentrism in any philosophical sense, but it would remind us that nature does not conform to human ideals of symmetry. The cosmos may be more irregular, more textured, and more complex than our simplified models allow. Scientists have begun exploring how to reconcile the KBC void with the cosmological principle. One possibility is that the principle holds statistically, even if not locally. In this view, large voids and clusters are natural fluctuations within an otherwise uniform universe, outliers rather than exceptions. The principle remains valid on scales larger than any single void. Another possibility, more radical, is that the principle fails altogether on observable scales, requiring a new framework for cosmology that allows for significant regional differences. Some researchers use models like the Lemaitre-Tolman-Bondet solutions to describe such inhomogeneous universes, where density varies with distance but overall symmetry remains. These models can mimic the observed acceleration of cosmic expansion without invoking dark energy, suggesting that our apparent acceleration might partly reflect our position within a vast underdense zone. Whether or not these models are correct, they demonstrate the flexibility of cosmological thought when faced with new evidence. Challenging the cosmological principle is not heresy, it is progress. Every advance in science begins with questioning the assumptions that once seemed unshakable. If future observations confirm that our local region is indeed exceptional, cosmology will adapt, incorporating that complexity into a richer understanding of the universe. Perhaps the universe's beauty lies not in its perfect symmetry, but in its imperfections, the subtle deviations that reveal its dynamic nature. The cosmological principle, long a guiding star of theory, may one day be replaced by something more nuanced, a recognition that uniformity is an illusion of scale, and that the universe, like everything within it, is wonderfully uneven. The vast cosmic voids that fill the universe today trace their ancestry back to the tiniest possible scales, to quantum fluctuations that existed long before galaxies, stars, or even atoms. In the first fraction of a second after the Big Bang, the universe underwent a brief but extraordinary phase known as inflation. During this period, space itself expanded exponentially, stretching from subatomic dimensions to astronomical scales in an instant. The process magnified microscopic quantum ripples into macroscopic variations in density, tiny differences in how matter and energy were distributed across the newborn cosmos. These fluctuations were minuscule at first, but they became the seeds of everything that followed. Where the energy density was slightly higher, gravity would later draw more matter, forming galaxies and clusters. Where it was slightly lower, expansion would proceed more freely, eventually creating the great cosmic voids that dominate space today. In this way, the emptiness surrounding our galaxy is not a product of chaos, but a direct descendant of quantum uncertainty. Inflation ensured that these initial fluctuations were frozen into the very fabric of space-time. Quantum mechanics dictates that even the vacuum cannot be truly empty. It teems with virtual particles and energy fluctuations that appear and vanish on unimaginably short timescales. During inflation, these quantum tremors were stretched across the universe, leaving faint imprints that persist to this day. The cosmic microwave background still carries their signature as subtle variations in temperature and density. Those irregularities represent the earliest known evidence of quantum processes influencing the structure of the macroscopic universe. It is a breathtaking thought. The distribution of galaxies, the shape of clusters, and even the KBC void itself all owe their existence to random quantum events that occurred in the first instant of time. This connection between the microscopic and the cosmic is one of the most profound insights of modern physics. It shows that the laws governing the smallest particles also shape the largest structures, uniting the quantum world with the grand architecture of the universe. Every void is thus a fossil of those original fluctuations, a vast stretched-out echo of the quantum foam that once filled the cosmos. Yet despite this elegant picture, many questions remain. We still do not fully understand what drove inflation, or what physical field caused space to expand so violently. Some theories suggest that inflation was powered by a hypothetical scalar field called the inflaton, whose energy temporarily dominated the universe. Others propose that inflation may be part of a broader multiverse, with different regions undergoing independent expansions. If so, our void could be one of countless outcomes produced by quantum randomness on an even grander scale. Regardless of the mechanism, the principle remains the same. The large-scale emptiness of space began as tiny fluctuations in the quantum vacuum. Over billions of years, those small imbalances evolved into the vast web of filaments and voids we observe today. The regions that began with slightly higher density became the bright threads of galaxies, while those that began with less matter became the silent basins of cosmic emptiness. In this sense, voids are not anomalies but natural expressions of the universe's quantum beginnings. The KBC Void, then, can be seen as a bridge between the subatomic and the cosmic. Its very existence tells us that the universe retains memory of its earlier state. When we map the large-scale structure of space, we are effectively reading the fossilized imprint of quantum behavior magnified across unimaginable distances. It is as if the uncertainty principle itself has been written into the stars, the galaxies, and the dark spaces between them. The realization that nothingness arises from something as fundamental as quantum fluctuation gives new meaning to emptiness. It is not the absence of creation, but one of its earliest expressions. Every void, including the one that surrounds us, carries within it the whisper of the universe's birth, a silent record of the moment when physics blurred the line between randomness and design. When we speak of emptiness in the universe, we are not referring to a true void in the absolute sense. Even the most desolate regions of space are not completely empty. They contain a faint whisper of existence, dark matter, diffuse gas, stray photons, and the subtle curvature of space-time itself. The structure of nothingness is therefore paradoxical. It is a framework defined by absence, yet it shapes everything that exists. In the cosmic web, voids occupy most of the universe's volume, surrounding filaments and clusters like the gaps in a vast three-dimensional lace. They form an interconnected network of hollows that stretch across billions of light-years, touching and merging like bubbles in a cosmic foam. The emptiness between galaxies is not uniform but textured, filled with gradients of density and gravitational potential. Within this invisible architecture, the laws of physics still operate, sculpting patterns in the dark. A typical void contains only 1/10 the matter found in an average region of space. Most of that matter is dark, unseen except through its gravitational effects. The few galaxies that inhabit these lonely expanses are often small and faint, their light struggling to cross the great emptiness that separates them. Yet the distribution of these galaxies reveals much about the structure of the void itself. Astronomers find that even within apparent emptiness, there are subtle flows of matter, galaxies drifting slowly along gravitational gradients, streams of gas threading through invisible channels of dark matter. Voids are not static holes, but evolving entities that expand and interact with their surroundings. As the universe ages, dense regions collapse into tighter knots, while voids grow larger, pushing matter outward and merging into ever wider cavities. The KBC Void is a prime example of this process taken to its extreme. It may represent a region where the expansion of space has outpaced the gathering of matter for billions of years, leaving behind a vast underpopulated basin surrounded by the dense walls of distant superclusters. Despite their emptiness, voids are among the most important structures in cosmology. They define the contrast that allows the universe's large-scale pattern to exist. Without them, the distribution of matter would be flat and featureless. Voids provide the negative space that gives form to the cosmic web, much as silence gives rhythm to music. They also serve as laboratories for testing fundamental physics. Because they are dominated by dark energy and low gravitational fields, even slight deviations from the standard cosmological model would appear more clearly there than in dense regions. The way light bends as it travels through a void, the phenomenon known as weak lensing, offers clues about the nature of dark matter and the geometry of space. The motion of galaxies along a void's boundaries reveals how gravity competes with expansion. In this sense, the structure of nothingness is a map of cosmic dynamics written in negative space. Philosophically, the existence of structured emptiness challenges our intuitive notions of reality. We tend to equate presence with meaning and absence with nothingness. Yet the universe suggests the opposite. Emptiness is not the absence of structure, but one of its essential components. The great voids are not void of significance. They are active participants in cosmic evolution, shaping how matter gathers and how light travels. In their vast stillness, they embody the equilibrium between expansion and gravity, between creation and dispersal. When we study the KBC Void and others like it, we are learning not only about the cosmos, but about the nature of contrast itself. Everything we know exists because of what is not there. The spaces between galaxies give them shape, just as the gaps between stars make constellations visible. The structure of nothingness is thus the architecture of everything. What appears to be emptiness is, in truth, the universe's silent design, the invisible foundation upon which all matter, motion, and meaning rest. From the standpoint of standard cosmology, the existence of the KBC Void appears highly improbable. Computer simulations based on the lambda cold dark matter model predict that large-scale structures should follow well-defined statistical patterns. Small voids, spanning tens or hundreds of millions of light-years, are common outcomes of cosmic evolution. They form naturally as matter flows toward denser regions, leaving gaps behind. But a void extending nearly 2 billion light-years across, with a 20% drop in average density, stretches the limits of what these simulations can produce. In statistical terms, such a region lies far beyond the realm of ordinary cosmic variance. It is as if one found an ocean on a planet expected to be entirely desert, a rare but not impossible deviation that demands explanation. To quantify how unlikely this is, cosmologists use probability distributions that describe how density variations should behave on large scales. These distributions are derived from the physics of the early universe, where quantum fluctuations followed a near-perfect Gaussian pattern. According to these models, a void as deep and extensive as the KBC one would occur less than once in the entire observable universe. In other words, if the simulations are correct, our location represents an extreme statistical outlier. Such an outcome forces scientists to consider two possibilities. Either we are extraordinarily lucky to live in such a region, or our model of structure formation is incomplete. The first option, while not impossible, feels unsatisfying. Science generally resists explanations based on coincidence, preferring mechanisms to luck. The second option is therefore more compelling. It suggests that something about how we simulate the universe may be missing an important factor. One potential issue lies in the assumptions built into the models themselves. Most large-scale simulations begin with uniform initial conditions and evolve them according to known physics: gravity, dark matter dynamics, and cosmic expansion. They assume that over sufficiently large volumes fluctuations cancel out, producing statistical uniformity. But if the early universe contained slightly non-Gaussian fluctuations, departures from perfect randomness, then large voids could be more common than expected. Detecting such deviations would offer a rare glimpse into physics beyond the standard model, possibly revealing how inflation unfolded in its earliest moments. Another explanation could involve feedback processes during galaxy formation. As stars and black holes form, they release tremendous energy that can push gas and matter outward, subtly reshaping the large-scale distribution. If these effects accumulate over billions of years, they might amplify the size of voids more than current models allow. Even so, the magnitude of the KBC void remains difficult to reconcile with standard predictions. Its very existence challenges our understanding of how uniform the universe truly is. The statistical improbability of our position raises deeper philosophical questions about observation and selection. It is possible that we notice such anomalies precisely because we exist within them. If life requires long-term stability and relative isolation from violent cosmic events, then regions like the KBC void might be unusually conducive to it. Dense regions of the universe experience frequent galaxy collisions and intense radiation from active quasars, conditions that could disrupt habitable systems. By contrast, a quiet void provides a calm environment where galaxies evolve undisturbed. If that is true, then our apparent improbable location might be a form of anthropic selection. We observe the universe from a rare environment, because such places are the only ones where observers can arise. This perspective, though controversial, has gained traction as a way to explain improbable cosmic coincidences. It doesn't imply design, only that observation itself is biased by survival. Still, even with such reasoning, the scale of the KBC void demands attention. If further surveys confirm its dimensions, cosmology will have to adapt, either by expanding its statistical models or by acknowledging that large-scale inhomogeneities are a natural part of the universe's texture. What we once considered impossibly rare may turn out to be simply uncommon. The improbable, once examined closely, often becomes another expression of cosmic diversity. Perhaps the universe is not as statistically neat as our equations prefer, but far more varied and intricate balance between order and anomaly. The KBC Void, improbable as it seems, might simply be the universe reminding us that even the most elegant models cannot predict every shape that reality chooses to take. In the vastness of space, the great cosmic voids may seem like empty wastelands, yet they are among the most valuable laboratories in the universe. Because they contain so little matter, they offer unique conditions for testing the laws of physics with minimal interference. In dense regions, clusters, filaments, and galaxies, gravitational interactions, magnetic fields, and radiation create a chaotic blend of effects that obscure subtle phenomena. Voids, by contrast, are pristine. Their isolation allows cosmologists to study how space expands, how dark energy operates, and how gravity behaves when left almost entirely alone. In a sense, these immense basins of near-nothingness function as the universe's control experiments, revealing the purest form of cosmic evolution. One of the most intriguing aspects of voids is that they are dominated by dark energy. In denser areas, gravity resists expansion by pulling matter inward, but in voids, where matter is scarce, dark energy's repulsive influence reigns unchecked. This makes them natural test sites for studying cosmic acceleration. By observing how galaxies on the edges of voids move over time, astronomers can measure how fast space itself expands in these regions. If the rate differs from the predictions of general relativity or the standard cosmological model, it could point to new physics, perhaps a modification of gravity or an interaction between dark energy and dark matter. Some researchers propose that dark energy may not be constant but vary with density, strengthening in empty regions and weakening in crowded ones. Voids could therefore hold the key to understanding the very force driving the universe's expansion. Another valuable property of voids is their cleanliness. Because they lack the gravitational clutter of massive structures, light travels through them with minimal distortion. This makes them ideal for studying weak gravitational lensing, the subtle bending of light caused by intervening mass. By examining how background galaxies appear, stretched or magnified as their light crosses a void, scientists can map the underlying distribution of dark matter. Such measurements provide crucial constraints on cosmological parameters like the matter density and the amplitude of primordial fluctuations. They also help test whether gravity behaves differently in low-density environments. Some alternative theories of gravity predict deviations from Einstein's equations precisely in such regions where the usual gravitational screening effects disappear. If these deviations exist, voids are where they will be found. Observations of voids also contribute to understanding cosmic flows, the large-scale motion of galaxies under the combined influence of gravity and expansion. Within a void, galaxies drift outward as space expands faster than in surrounding areas. By measuring these peculiar velocities, astronomers can infer how mass is distributed across vast distances. Comparing observed flows with those predicted by simulations allows scientists to test the accuracy of cosmological models. The KBC Void, in particular, provides a compelling opportunity for such studies due to its enormous scale and proximity. It acts as a natural laboratory situated in our cosmic backyard, allowing detailed observation of local expansion, structure formation, and galaxy evolution. On smaller scales, void galaxies themselves are valuable test subjects. Isolated from frequent interactions, they evolve more slowly, offering insight into how environment shapes galactic growth. Their chemical composition, star formation rates, and morphology differ noticeably from galaxies in dense regions. By studying these outliers, astronomers can disentangle the intrinsic processes of galaxy formation from the effects of environment. Even the intergalactic gas that threads through voids is scientifically rich. Although diffuse and faint, it carries signatures of the universe's chemical history elements forged in ancient stars and dispersed through cosmic winds. Sensitive instruments can detect this material through absorption lines in the spectra of background quasars, revealing how matter cycles through space over billions of years. In this way, voids allow us to trace both the physical and chemical evolution of the cosmos. Ultimately, what makes voids so compelling as laboratories is their simplicity. They strip the universe to its essentials, exposing the raw interplay between geometry, expansion, and the invisible forces that govern everything. The absence of matter becomes a kind of clarity, a stage where the fundamental rules of reality can be observed without distraction. The KBC Void, far from being a cosmic anomaly, may thus be the universe's most eloquent classroom, a vast and silent space where the laws of creation reveal themselves in their purest form. Inside the vast emptiness of cosmic voids, galaxies lead quiet and solitary lives. Unlike their counterparts in dense clusters, which constantly interact, merge and collide, void galaxies evolve in near isolation, undisturbed for billions of years. This separation offers astronomers a unique glimpse into how galaxies develop when left to the forces of nature alone, free from the gravitational chaos of crowded environments. These lonely systems are the hermits of the cosmos, rare, faint and widely spaced, yet essential for understanding how environment shapes the architecture of the universe. Most galaxies in voids are small and dim, often irregular in shape. They lack the massive bulges and tightly wound spiral arms characteristic of galaxies in denser regions. Because they form in areas with low matter density, they accumulate gas more slowly and experience fewer external triggers for star formation. As a result, they tend to be rich in hydrogen but poor in heavy elements, suggesting a slower and more pristine evolutionary path. Their stars are often younger and bluer, still burning through the primordial gas that has fueled them for eons. In this sense, void galaxies serve as living fossils, preserving conditions reminiscent of the early universe. Studying them allows scientists to observe galactic evolution under conditions close to the cosmic baseline, before interactions and mergers reshaped the majority of galaxies elsewhere. Isolation, however, does not mean stagnation. Even in the deepest voids, gravity and dark matter sculpt the faint skeletons of structure. Small filaments of gas and dark matter thread through the emptiness, linking the sparse galaxies into loose networks. Along these threads, galaxies can still exchange material through slow, graceful flows of gas, or occasionally merge in rare encounters. Such events, though infrequent, can dramatically alter their evolution, igniting bursts of star formation and reshaping morphology. Yet compared to the violent dynamics of clusters, these processes unfold on a far gentler scale. Time moves differently in a void. Evolution proceeds not through collisions but through quiet persistence. Observations of void galaxies have revealed intriguing anomalies that challenge conventional models of galactic growth. Many of them exhibit unexpectedly high rotation speeds relative to their visible mass, suggesting that dark matter dominates their dynamics even more strongly than in typical galaxies. Some possess extended gas disks that stretch far beyond their luminous cores, indicating that star formation has been suppressed or delayed. Others contain unusually large reservoirs of unprocessed hydrogen, hinting that the conversion of gas into stars is inefficient in such sparse environments. These peculiarities make void galaxies crucial for testing theories of dark matter and baryonic feedback. Because their isolation reduces external interference, any discrepancies between prediction and observation point directly to intrinsic physics rather than environmental effects. There is also an aesthetic and philosophical fascination in these cosmic loners. Each one is an island of light adrift in an ocean of darkness, a self-contained world evolving in silence. Their existence reminds us that even in the emptiest reaches of the cosmos, creation persists. Stars are born, die, and scatter elements into space, slowly enriching their surroundings. In their faint glow, we see the resilience of matter, the universe's unending drive to structure itself, even where the odds seem impossible. The KBC Void, with its immense scale, hosts countless such galaxies scattered across its volume. To most telescopes, they appear as faint smudges barely distinguishable from the background, yet together they trace the hidden contours of the void's interior. Their distribution maps the faint filaments that remain inside the underdense region, marking where gravity still holds sway against expansion. Each galaxy acts as a beacon, illuminating the invisible skeleton of dark matter. By studying their positions, velocities and properties, astronomers can reconstruct the three-dimensional structure of the void itself, turning these quiet galaxies into signposts of the universe's grand geometry. In a way, galaxies in isolation reveal something essential about the cosmos, that life and structure thrive not in spite of emptiness but because of it. This silence of the void provides the space for growth, the calm in which stars can form without disruption. The universe, it seems, creates both density and solitude as partners in its design. In the deep stillness of intergalactic night, these faint galaxies continue their slow, graceful evolution testaments to the quiet persistence of creation in the most unlikely of places. Even within the vast emptiness of the cosmic voids, the universe refuses to be truly barren. Scattered through these immense expanses are colossal structures, superclusters that rise like islands of matter in an ocean of darkness. These immense conglomerations of galaxies' gas and dark matter are the largest gravitationally bound systems known, stretching hundreds of millions of light-years across. Within the KBC Void, they form the distant walls and subtle filaments that define its boundaries, marking where the underdense region ends and denser space begins. The Laniakea supercluster, to which our Milky Way belongs, is one such structure. It encompasses over 100,000 galaxies and spans more than 500 million light-years, yet it floats along the rim of the KBC Void like a continent bordering a cosmic sea. Laniakea's defining feature is its gravitational flow galaxies within its domain drift toward a central region known as the Great Attractor, a massive concentration of matter that anchors the surrounding cosmic terrain. This gravitational river organizes the motion of entire galactic populations, channeling them along invisible paths that curve through the void's edge. Beyond Laniakea lie other superclusters, such as Perseus Pisces, Coma, and Shapley, each forming part of the immense lattice that frames the KBC Void. Together they weave the boundary of the underdense region, enclosing it like the rim of a vast basin. Between these dense walls the void stretches out, silent and largely empty, its centre sparsely populated by faint galaxies adrift in expanding space. The coexistence of superclusters and emptiness creates a striking cosmic contrast, a universe composed simultaneously of overabundance and absence. The presence of superclusters along the edges of voids reveals how structure grows in a dynamic balance between gravity and expansion. Matter flows out of emptier regions and accumulates along the boundaries, forming the immense filaments and clusters that mark the cosmic web's brightest lines. Over billions of years, this process has sculpted the universe into its current configuration, a network of dense ridges enclosing hollow interiors. The KBC Void, in this sense, is not an isolated anomaly but a natural product of that ongoing migration of matter. Its surrounding superclusters are like the raised walls of a great geological basin, formed by the gradual movement of cosmic material over time. Yet the KBC Void is unusual in size and symmetry, suggesting that its formation involved more than ordinary gravitational drift. Its boundaries appear smoother and more continuous than those of smaller voids, indicating a long and stable evolution. Within these borders, smaller substructures, miniature filaments, faint groups of galaxies, and thin streams of dark matter still exist, hinting that even emptiness retains traces of the universe's larger order. These subtle filaments connect the isolated galaxies within the void to the outer walls, forming tenuous bridges of matter that maintain cosmic coherence. One of the most fascinating aspects of studying superclusters within or near voids is understanding how they influence cosmic motion on enormous scales. The gravitational pull of these dense regions extends far into the surrounding emptiness, affecting the trajectories of galaxies millions of light-years away. Our own galaxy, along with others in the local group, moves toward the Great Attractor at hundreds of kilometers per second, a motion shaped by the mass distribution around the KBC Void. This interplay between attraction and expansion defines the cosmic landscape, a dynamic equilibrium between the pull of clustered matter and the push of the void's rapid expansion. From a scientific standpoint, superclusters act as markers that help define the size and shape of the void. By mapping their positions, astronomers can trace the contours of the underdense region with precision, creating a three-dimensional model of the local universe. From a philosophical standpoint, their existence within a sea of emptiness illustrates the universe's tendency toward contrast. Where there is great emptiness, there is also great structure. Where matter thins out, the remaining mass gathers more tightly. The desert of the void makes the superclusters stand out all the more vividly, their light and gravity magnified by the surrounding absence. The KBC Void and its bordering superclusters thus represent two extremes of the same cosmic process. One defined by scarcity, the other by abundance, both essential to the universe's architecture. In the silent expanse of intergalactic darkness, these colossal structures are reminders that even the deepest voids are never truly empty. They are framed, defined, and given meaning by the matter that surrounds them. The discovery of the KBC Void and the growing awareness of our position within it reach far beyond the confines of astrophysics. They challenge how humanity understands the universe and itself. To realize that our galaxy drifts in the center of a vast underdense region nearly 2 billion light-years wide reshapes not only cosmological models, but philosophical assumptions about our place in existence. It forces scientists to confront the limits of their measurements and thinkers to reconsider the meaning of cosmic perspective. The void is not merely an astronomical curiosity, it is a mirror reflecting the boundaries of human knowledge and humility. For cosmologists, the implications are both technical and profound. If the KBC Void significantly influences local measurements of cosmic expansion, then one of the universe's most important constants, the Hubble constant, may not be constant after all, at least not from our point of view. It would mean that observations taken from within this vast bubble cannot be directly compared with those made elsewhere. The assumption of large-scale uniformity, the foundation of modern cosmology, would have to be revised or refined to include environmental context. The equations of the universe would need to account for the geometry of our surroundings, acknowledging that the cosmic landscape affects what we see and how we measure it. Such a shift would ripple through every branch of astrophysics, from models of dark energy to estimates of cosmic age. Even small adjustments to expansion rates could alter the timeline of star formation, the evolution of galaxies, and predictions for the universe's ultimate fate. Yet the implications extend beyond science. The realization that we inhabit a vast void invites a profound sense of perspective. Throughout history, humanity has repeatedly discovered that it occupies no central or privileged position in the cosmos. Each revelation, from the heliocentric revolution to the discovery of galaxies beyond the Milky Way, has humbled our view of ourselves. The KBC Void continues that tradition, revealing that we live not in the dense heart of the universe, but in one of its quietest suburbs. This isolation does not diminish our significance. Rather, it enriches it. It shows that consciousness and complexity can arise even in the most tranquil corners of creation. From a philosophical viewpoint, the void highlights the paradox at the heart of existence, that emptiness and fullness are inseparable. The same physical laws that create clusters and galaxies also carve out the spaces between them. Structure and void are two sides of the same cosmic equation. Without emptiness, there could be no form. Without expansion, no cohesion. Our location within a vast cavity thus symbolizes a universal truth, that life and meaning can emerge even amid apparent absence. In a poetic sense, the void becomes not a symbol of nothingness but of potential, a canvas upon which the universe writes its most delicate patterns. The broader implications also touch on the future of scientific discovery. As observational technology advances, new surveys will map the distribution of galaxies with greater precision, revealing whether the KBC Void is unique or one of many large-scale depressions in the cosmic web. These findings will determine whether our local environment is an outlier or part of a broader pattern, and whether cosmic uniformity is an illusion born of limited perspective. Whatever the outcome, the investigation will deepen humanity's understanding of how the universe organizes itself across unimaginable distances. The KBC Void serves as a reminder that even the most advanced theories are still approximations, models carved from incomplete data. It encourages a kind of intellectual humility, the recognition that every measurement, every observation, is filtered through the lens of locality. To know the universe truly, we must first understand where we stand within it. In the end, perhaps the greatest implication of the void is existential rather than scientific. It reminds us that isolation does not mean insignificance, and that silence does not imply emptiness. The same cosmic forces that sculpted galaxies and clusters also shaped the vast hollows between them, balancing presence and absence in a grand harmony. Living within such a structure, humanity occupies a delicate middle ground between matter and void, certainty and mystery. The KBC Void, in all its immensity, becomes a metaphor for our search for understanding. We peer outward into darkness, not to escape the emptiness, but to realize that it is part of what makes the universe and us whole.